to our second speaker, Dr. Eslami. He's going to talk about Saline water intrusion in the Mekong and the system perspective for climate adaptation in the data. And it seems like it's a great segue. They will talk about Saline water intrusion, and so he's going to talk about that in more detail. All right.
Good morning, everyone. This is a much fancier stage. I'm assuming we get a concert later like the guys who were here yesterday. Thank you very much to the Rosenberg Forum for inviting me, and I'm hoping after a presentation from Professor Fuchin I can build something on that one on the topic of salt intrusion and system perspective. This is a joint presentation with Frinda, who I've lost. She was, oh yeah, there. So we quickly touch on the topic of salt intrusion, but we go a little bit deeper in that, and then come up with a Mekong system understanding from a delta perspective and link that to socioeconomic impacts. That's where Frinda takes over. And then we go back to a proposal for a system perspective for the deltas worldwide. So many challenges in the Mekong Delta, but it was mentioned over the past presentations, but we look into the topic of salinity, which basically is the key to land use change in the Mekong Delta. So if we look at salt intrusion, Mekong or anywhere, it's a competition between river and sea. It's influenced by tides, by sea level rise, by wind, by waves, by ocean surges, fluvial discharge, precipitation, and also anomalies due to climate change, by human impact in agriculture and water demand, fluvial sediment starvation and sand mining that lead to erosion, and increased salt intrusion. There's also groundwater extraction, and that leads to land subsidence, and groundwater extraction that could lead to salt intrusion in the groundwater system. So a couple of concrete scientific steps. If we take one station, as we see there, and look at salinity over the last 20 years, we do see a very clear trend of increasing salinity. We look into a couple of things. Freshwater supply. If we look at, for instance, the station Kratie in Cambodia, which is like 250 kilometers from here upstream, and look at dry season discharge, we see a clear increasing trend of discharge over the past 3 decades. So that doesn't explain the salt intrusion problem. If we look at ocean forces and we take one station near the coast and look at water level signals, we actually, without any analysis, we can see a slight increase in the sea level rise trend. And if we analyze and get the tidal amplitude from that, we also see a slight increase in tidal amplitudes. So there's a question mark there. But if we move inside the delta about 80 kilometers and we take the same signal for water level, even without any analysis, we see a massive change in the tidal signal. And if you analyze that and get the tidal amplitudes from that, we do see a very clear deviating trend from the sea level rise within the delta. And in our opinion, that's what explains everything about salt intrusion and many other processes. So basically, if you look at the topic of salt intrusion, that might go back to Edward's point. There is sea level rise, a few millimeters per year. There is land subsidence that is centimeters per year, order of magnitudes larger. Then we have sediment trapping by upstream dams and excessive sand mining. These two result in river bed erosion and river bank erosion. That leads to increasing tidal range within 2 centimeters per year over the last 2 decades, 2 centimeters per year. And these together result in increased salt intrusion. And if we quantify the relevance, relative sea level rise is responsible for nearly 5% of this, and 95% is associated to internal processes such as sand mining and upstream dams, basically riverbed erosion. And if we go back to 2016, when there was a massive salt intrusion event, this was the realized salinity. If the riverbed levels had not changed by the time, in some places, salt intrusion would be as much as 20 kilometers less. So that brings us to this overall system. image, that we have a couple of millimeters of sea level rise, a couple of centimeters of increasing tidal amplitude, trends in fluvial discharge and fluvial sediment, erosions of 10 to 15 centimeters per year in estuarine riverbeds, subsidence in the order of centimeters per second, per year, sorry, and well, we see salt intrusion trends of 0.2 to 0.5 PSU per year. And if we add all of these drivers together in a sophisticated 3D model of the entire Mekong Delta, we come to different scenarios of salinity, which is slightly different than the approach of Professor Fuqian, but it's not too far. This is a bit slightly more detailed and focused on the delta itself, but uses the same principles. I bring it here. If we only look at climate change, by the year 2050, actually salinity increase. So the y-axis is the increase in saline water in affected areas. It actually stabilizes if it's only climate change. If we add extraction-induced, spatially varying land subsidence over the entire delta, that raises a few percentages. If we add riverbed erosion, that massively increases. And if we add scenarios of extreme sea level rise by 2050, that also provides additional scenarios and environmental pathways. There were talks about seasonality, so I don't talk too much about that, but one point I want to make, even with, again, the 2016 extreme event, salinity reached near Can Tho, but more than 50% of the time it was far from Can Tho. And if we look at it, it's a very big problem, but over a very short period of time, and this is something to keep in mind. And all of these analysis was made possible using this very sophisticated 3D model, which some of the tidal signals, I have this in this graphics. And, but as physical scientists, our work doesn't end here, and in a true spirit of interdisciplinarity, we try to team up with a true economist and see how we can deploy a very sophisticated numerical model from our perspective and link it to economic patterns. Frinda?
Thank you so much, Sepehr, for letting me share the slot with you, and also for the Rosenberg Forum organizers for having me here. So when I first started thinking about this project, I'm going the wrong way. Perfect. When I first started thinking about this project, my research question was, can we say something about how households have adapted to this phenomena over the last 10 years, and whether we as economists can say something about what would optimal policy look like in this scenario. But when I started answering this question, I realized that my ability to answer this question was limited by my training as an economist. Because what we tend to do is, when we are studying complicated environmental phenomena that are not rainfall or temperature, we rely on monitoring station data and do very naive interpolation of observed salinity to points where we do not observe it. And as Sepehr's presentation has shown, that would be a mistake. And I realized that it was a mistake as well, which is why we teamed up together to use the model that has been created to look at salinity intrusion over time and across space by taking into account the complicated systems within the delta, and use that time series and combine it with household level panel data to see how households have adapted. What the econometric techniques allows you to do, because of the panel data component, is to get to a causal estimate. So what we do is basically we see if the same households over time received an increasing level of salinity, and we control for all other household characteristics, what impact would they have and what would they do in response to that salinity. What we find is the delta, even though has experienced salinity over the past as well, still remains highly vulnerable to saltwater intrusion. No one is shocked to know that rice is super vulnerable to salinization. So we do see reductions in the winter-spring crop, which is like the winter crop, which is the most important crop. But more than that, what I want to highlight is that aquaculture also faces extreme income reductions for households. And this is important caveat to understand, because often we look at aquaculture as a response or a different occupation that households can do when they are faced with salinity, but actually they remain highly vulnerable to salinity shocks as well. When households face these income reductions, what they do is, the first thing they do is basically restrict migration. So they hold back labor within the households and rely heavily on existing remittances. And this just doesn't stop for migration. In fact, there is very limited localized labor reallocations as well. In fact, what we observe is that women actually pull out of manufacturing and expand agricultural hours. What I want to highlight here is that what this represents is that at least until 2018, salinization did not represent a shock that could lead the Mekong Delta into a pathway of structural transformation into more productive activities, but more seemed like constrained adaptation that households were undertaking because they were facing extreme income shocks. But we can actually move beyond these short-term adaptation estimates and also look at optimal policy. Yesterday we had a lot of conversations about infrastructure, but when economists and physical scientists work together, we can do much more. So what we here try to do is to get an estimate of how much these infrastructural barriers are contributing to resilience within the Delta. So we run the model, but this time we remove the sluice gates from the model and we see how much the salinity would have expanded. And when we do that, we can use the econometric estimates and get values of how much these sluice gates were preventing. And the numbers are quite encouraging for rice. So it does seem that rice loss is massively prevented by these sluice gates, but not aquaculture. And there are, and we can get upon this later in the discussion, even within the Delta, many winners and losers of different wards that actually win because of these sluice gates, and others whose income would have increased in the absence of these sluice gates. What I want to leave at is that infrastructure is important, but it's also important to understand for what infrastructure is actually working and the need for complementary policies that could work along with this. So right now we are working on extending the paper to also look at more contemporary insights and also develop a structural model of land use changes and basically see if we make land use flexible, will we actually prevent much more than infrastructure. And so I would like to leave on the note that yesterday we had discussion about what is applicable to what delta. This is applicable to the Mekong Delta, but to understand whether this would work in other deltas, it is important to have a more systematic approach to understanding what are the systems in place, physical and economic, in other deltas, and for that, I will bring back Sepehr.
So we've identified a bit of a gap between physical sciences and social sciences, and for that we went through a couple of years of a mental exercise with some true scientists, not me, but others, and we came up with a system perspective that could bridge this gap. We identified over the entire deltas that we studied 10 drivers of change that are common between deltas. In these 10 drivers, we separate them between climatic or natural processes and anthropogenic processes. So there's 3 of them, and we've separated climate change and sea level rise. Don't blame me, we have a reason for it I can explain, but basically it falls in that category. And then we have anthropogenic processes. And then we link them one by one to their direct, the top table, indirect, the middle table, and socioeconomic drivers, socioeconomic impact. So direct, indirect, and socioeconomic. When it comes to socioeconomic, basically it touches upon everything. But when we separate direct and indirect, it doesn't say anything about the magnitude. Sometimes an indirect impact could be larger than a direct impact. But that links these drivers to their impacts. And then we also mapped these drivers in space and time, which was also a topic we came up yesterday. So some of the processes such as climate change, they work in the global scale and in the decades to centuries scale, and then other drivers such as sand mining or groundwater extraction or natural subsidence in the smaller scale and in the shorter time scales. So we used this framework and we tried to address 3 deltas, Mekong, Ganges, Brahmaputra, and Nile. And we took threats to these deltas and tried to link them to their drivers. And we see quite a separation. So for instance, I just take Mekong, number 10 is sand mining. And we see that in the Mekong, it touches upon a lot of the threats. We go to GPM, that goes only to 2 threats. And when you go to the Nile, it's irrelevant. So that gives a little bit of a tool for us to discuss and bridge this gap. between the physical sciences and social science, and maybe even provide some sort of a stakeholder engagement tool. That's something that I would like to go back to that later. So some concluding remarks: deltas are complex, talked about that. They have common drivers of change, but every delta is unique in its own way. Climate impact cannot be independent of local drivers of change. And when we talk about effective adaptation planning, we believe is built on 3 pillars, which is sound scientific system understanding, which we think it's undervalued in these adaptation efforts, informed communities, and their political representation. So this sound scientific system understanding that we try to advocate for can be semi-quantitative, but it has to be a solid conceptual mapping, which can go into detail later. And that highlights the significance of interdisciplinarity, and also it may provide options at smaller scale that can lead to with higher implementation likelihood that can lead to longer-term climate resilience. So getting back to some of the discussions that was yesterday, indeed, we think that it is important to think big, and in order to build trust between communities and policymakers, start small. And with that, I would thank you very much.
All right. Thank you.